We're going to be reasoning with algebraic expressions. What we just got done doing, that number trick, we're going to see why it worked. So in question 1, algebra and number magic. It wasn't magic, it was algebra, and we're going to use algebraic proof to show how I did at first and then how you figured out later how we could guess these numbers a lot easier than going through this whole process. So question number 1, it says there is a simple way to discover start numbers and to think about the situation that we did. Subtract 1 from the end number and divide that result by 2. We eventually figured that out. Explain why that decoding strategy works, and proving that it will always work requires some algebraic reasoning. So here's where we are. We're starting a new lesson. This is a row 5 investigation. In this row investigation, we're going to be dealing with a lot of algebra. So we're going to have to brush up on some skills. I can already tell from 4th period and 5th period, we're not that good at squaring numbers. We're not that good at collecting numbers. We're not that good at factoring. But it's there. We have the skills to build upon. We just have to reinforce them. So we're on algebraic proofs. I have a word on the board here. This is a big, important word. Now I use GEMDOS rather than PEMDOS because I like grouping symbols better than parentheses. Any grouping symbol has to be done first. And the bell ringer that we did, remember that where I made you pick? Which one of these expressions gave you the right answer? It was about matching your order of operations correctly. So we're going to prove what we just did. In question A, if we're proving, one of the requirements is it must be general. So we're going to pick a number. A number, number starts with N, so I'm going to use the letter N because it must be general. So that's what they're saying in part A. Use the letter N to represent the start number and build an algebraic expression that shows the steps for calculating that result that you reported to me. Okay, so you guys got to pick any number. So any number is going to be represented by N. Now what's the first thing that we did to it in step 1?
Added.
So we're going to write that as N is what we started with, then we had to add 5. Now, here's the first big one that we get going in the right direction. After we added 5, we multiplied that result by 6. How do we have to write that so it gets done in the right order of operations? 6 parentheses N plus 5. If we don't get those parentheses in there, the order of operations will be out of order or wrong for our procedure here. Okay, so that's the first little hurdle. Next thing, we want to divide that result by 3. What's the best way to write that so that we can reason algebraically?
Over 3.
Over 3. You bet. So we want this, and I'm going to just extend it over here. It's 6 times N plus 5 divided by, is a fraction bar, 3. We'd want to really get away from symbols like divided by or times signs or even dots to represent multiplication. Those are kind of a hindrance when we try to reduce and use some algebra in these things. Finally, the last thing we're supposed to do, take that result and subtract 9. I could put parentheses or some type of bracket around this whole thing and then minus 9. That's okay. It doesn't hurt anything. Although, if you think about your order of operations, what's the last thing that's going to be carried out anyway?
Subtraction.
Subtraction is going to be the last thing. So do I need this here?
No, but it's nice for organization.
No, but it does help organize. So it's one or the other. I'm going to write it without because it's not necessary. And a lot of times if you keep putting things in that aren't necessary, it gets more and more cumbersome to work with as well. So this is what our expression looked like. We had a number. We added 5. We took that number times 6. Then we took that answer, divided it by 3, and finally we subtracted 9. All right, now we're at part B. Part B says, use what you know about algebra to write the final expression in part A, which was this expression here, in simplest form. And what relationship between the starting numbers and ending numbers is shown by the result. So, all right, here's what we had in part A. We ended up with 6 times N plus 5. All over 3 minus 9. Now in part B, we're supposed to take this and write it in a simpler form. Okay. Jenna's got an idea. David had an idea earlier. What's a first reduction that we can do? The 6 and the 3, right? We're going to be dealing a lot with fractions. When you have a 6 over a 3, what can you rewrite that as? 2 over 1. So the 3 goes into 3 once, the 6 becomes a 2 because 3 goes into it evenly. Now I'm going to rewrite that down below. It's 2 times n plus 5 minus 9. In most of our algebra, we're going to have a lot of fraction work. So we're going to have to remember how to reduce fractions and how to add fractions and multiply fractions. So a little review on reducing them. Now what can we do to help reduce? Okay. Distribute the 2. So we've got, if we distribute, it means we've got to take both of these and multiply times 2, which ends up with 2n plus 10 minus 9. So here we are simplifying this expression. But we got one more step to do. What else can we do? Subtract 9. We can collect our like terms. These two end up giving us just a 1. So no matter what number we started with, our final number was nothing more than twice what we started with plus 1. And you get the deal? After doing all this stuff that seems so complicated, right? In the end, all we did is we doubled it and added 1 to get our final number. That's what you reported to me. Now, let me come back and see this first. What relationship between the starting number? Okay, go ahead.
Why didn't you have to divide n plus 5? Divide by 3 or something?
Because we already did the division. What is 6 divided by 3? 2. Now it's gone.
But why didn't you have to do n plus 5 divided by 3?
Because I've already divided by 3. It doesn't say you divide multiple times. I don't distribute division through multiplication. The distributive property is probably one of the least completely understood properties that we have. You only distribute over addition subtraction. Here is a distributive property. There's a multiplication sign here, and we're distributing over addition.
To get it down.
But you don't divide and distribute division through multiplication.
Yeah, because that was stupid.
The 9 never was divided by 3. What's that?
Nothing like it.
There's Prince there. You asked me about the 9 being divided by
Yeah.
3. It was never divided by 3.
But you don't have the parentheses, but if I hadn't had.
Well, you can put these in here the way you wanted them.
Yeah,
Regardless, that 9 was never ever intended to be divided by 3. It was the result that was divided by 3, and in that result, we subtract 9. Okay? Now let's go to their part C, their line of strategy here. Can the relationship between the starting and ending numbers be used to find the starting number and only the ending number is known? So now they're coming back full circle. This is what I asked you to do in the beginning. I said, you give me your final number. When you gave me your final number, I had to do something to go back to your original number. Okay, so that's exactly right. I'm going to bring this back up here because this is what our coding was. Our coding is kind of what really happened to our number we started off with. We coded it by doubling it and then adding 1. Now they're asking us to decode it. If you decode it, you want to reverse it.
So subtract 1,
So I'm just going to use the word final. And what you just described to me is how to find the original number. First thing we have to do is subtract 1, and then we have to divide by 2. The final minus 1 divided by 2. So whatever number you fed me, I subtracted 1 divided by 2. Algebraically, this is what we're doing to prove it. You understand this is about mathematical proof. It must be general. If we solve it or we show somebody, it has to be in a logical, sequential, based on known facts, information. So everything we did here in part B better be based on known facts. It was division of fractions. It was distributive property. It was collecting like terms. All things that we've done. So that's part of it. Okay, so now I'm going to give you a little bit of time because in part D, you're supposed to change this pattern a little bit. Suppose that instead of dividing that result by 3, that step, I think it was the third step in this, you replace it with divide the result by 2. How would you change the procedure and the effect of decoding? So first of all, you have to figure out, if you change that line to divide by 2, how does it change the coding of your final number? And then, how do you decode it back? All right, so go ahead and work on that, and we'll report back in on it. No. Okay, so now you had a little bit of time to go through this. So everything was the same. We had 6 times n plus 5. This time we had to divide by 2 instead of by 3, then minus 9. So what was the first thing that you did algebraically to help you reduce or simplify?
Divided 6 by 2.
Okay, do your division. The 6 divided by 2 is nothing more than 3. So you had 3 times n plus 5 minus 9. Now what did you do?
Distribute the 3.
Distribute your 3, so it's 3n plus, did you get that figured out, Aaron?
Yeah.
15, good. That was the one spot that you had to make a correction on, right? Okay, now we want to collect our like terms. Caroline, you got that all subtracted out now this time?
Yeah, it's a 6.
Plus 6. Okay,
Oh,
so this is going to give you your final number. There's no more simplification you can do to this. I've had, and David did it, and someone else in the other period did it. They factored out the 3, or at least the 3 disappeared on it. Do you see how 3 factors out of them?
n plus 2.
Which is absolutely right. But it doesn't really help you in this coding and decoding. If I write it as 3 times n plus 2, is it easier now? You might argue it might be easier to do this, but is it easier to come back and solve it with a decoding process? Probably not. Someone might argue that's maybe a little harder. But whatever the case might be, we can do it either way. If I want to go back from the final, if this is what my final number is, then how do I get back to the original? So now let's decode. To decode, we first have to.
Minus the 6.
So whatever the final number is, subtract 6, and then
Divided 3.
Wait, the decoding helps you get to your final. What's your
now
conclusion?
you report to me a final number, then I can guess what your starting number was. That's what n is, your starting number.
Okay.
So basically, we can do it either way. It would be interesting to kind of do this one because I think that's what JC you more or less ended up with. If you do factor this thing like this, that's got to be your final. What's the first thing you have to do on this one?
Multiply times 3.
You got to get rid of your multiplication first, which means you'd have to divide by 3. If you divide both sides by 3, then you'd have n plus 2 equals the final number divided by 3. Now how to get rid of that 2? So n equals the final divided by 3 minus 2. Now I don't know which one's going to have a easier process for you. Either one would work. All right, let's go to the next one. Now the next one is basically just do it on your own and show me your answer. So again, I'm going to pause this, let you guys work on it for a few minutes, and we'll see if you can code it first, then decode it back. So write your expression out, simplify it, decode it.
Do we have to follow what they're saying in the box?
Caroline, what did you pick for a number?
I picked 7.
Caroline, we're going to do a proof. What are you going to pick for a number?
And
Caroline,
And
you can let her answer. She's
sorry,
fine.
Caroline, did we
N.
or 2 in English?
Caitlin, what do we do next to it?
yeah, that's you double it.
You double it. How are you going to write that when it's doubled? And how are you going to write that times 2?
I knew it would just.
You don't want to write anything other than what's the shortest way to write multiplication? 2n. Try to get rid of all those other dots and parentheses and time signs. Okay, so we just doubled it. Now, what do? Add 3 to the result, so just plus 3. So I did that. How do I make sure that that result gets multiplied by 5? What did you have to put in? Parentheses. This result always is going to imply special multiplication. Get your parentheses around it. Then finally, subtract 7. Now this is how we're going to try to get our final number. But they say simplify it, and you can find the code. So simplifying it, what's the first thing you had to do to simplify? Many of you said, I don't know how to simplify. Well, what is it? What's the first thing you do? Distribute. So that's 10n, and 15 minus 7 equals, use F for final, then collect your like terms. So your final number should have been simply 10 times your number plus 8. That wouldn't be terribly hard to calculate in your head. Now, that's how we coded it. So how do we decode? First thing we got to do to decode is what?
At minus 8.
So 10n equals the final minus 8, then?
Divide by 10.
And we've got it. Whatever our final number was, minus 8 divided by 10. Okay, we are not going to do question number 3. We're skipping it. We have one more question to do, and then we can listen all we want. Number 4, it's on sequences. Number 4, consider the sequence of square numbers that begin 0, 1, 4, 9, 16. Complete the following table and show how the sequence continues. So that's your first task. Take this chart, copy it down, and start filling in the blanks. N stands for the number. S of n stands for the sequence number. All the way out to the n for sure, and then we'll talk about the n plus 1.
How do you know what the rest of the numbers in the chart are?
Figure out the pattern. What is the pattern in this chart? Yeah, and they say the sequence of square numbers. If you read
Oh.
and you interpret, they many times will tell you how to find it. So what's under the 5? 25. Under the 6?
49. 64.
Okay. Now, we're going to prove this, so proving it can't be done with specific numbers, so now they're going to get general. So what should go under the n? N squared. That's all we do to find it. Remember, n stands for the term number. What term are we? The S of n stands for your sequence term that goes with it. What should go under the n plus 1 term? Now, let me back up a little bit. In part C, they're going to ask you about this, but what comes after the nth term? What comes next? Does that make sense to you? If we're at n, how do we get to the very next number? Consecutive number. So what goes under the sequence number? All right. Are the parentheses important?
No, because you can just do n squared.
We were right the first time, then I asked you, were the parentheses important?
No.
You're right the first time.
Yes, they are.
Yes, they are.
Very important.
You got to take whatever the number is and then square it. You do not get the same if you take your number, square it, and then add 1.
Well, you would for one. Technically.
Do you want it just for one specific number, or do you want it for all numbers?
That's why I was a little confused just to say.
Letter B, calculate the differences between consecutive terms in the sequence of square numbers. Read to understand that. What does it mean? Calculate the differences. What's that mean?
What's the subtraction mean?
Subtract. Between consecutive terms. What does consecutive mean?
The next one.
The next one. We all only have to do is find the difference between the terms. Consecutive terms. So they even gave a little example here. Take S4 minus S3. S4 minus S3. But it's always find your one on the right, subtract the one on the left. Find the difference. Subtract. So we're going to take these two and we're going to subtract them. What is 1 minus 0? We're going to take these two successive terms. 3. These two successive terms. Which is the point. We're going to find patterns on these. Okay? And then we got this break in here. That's what they're asking you. In part B, describe the pattern that develops in the sequence of differences. What are you seeing? What's the pattern that's developing? Yeah, we get consecutive odds. Our pattern is we get consecutive odds. Now, I already did part of what part C did. Part C says if n is the number, then n plus 1 represents the consecutive whole numbers in the difference table. Here it is. Now, all we've been doing is we've been finding the difference between these successive terms. How would it look if we generalize this and don't use specific numbers? What would it look like if we had to subtract these? Not a leap of faith, all you gotta do. What did we do to get 15? What did we do to get 13? What did we do to get 11? The one on the right minus the one on the left. The one on the right, n plus 1 squared minus the one on the left, n squared. What does that represent? The difference of consecutive terms. Now, don't get all crazy on me here, but here's how they represent that. S sub n plus 1 minus s sub n. What is the s sub n plus 1 term? What is the sequence number associated with the n plus 1 term? N plus 1 squared. That is going in for this. N plus 1 squared. What is the s of n represented by?
N squared.
N squared. It's the n term, but we want the s of n term, which is n squared. We're going to simplify this. When we simplify it, we should end up, no matter what numbers we subtract, we should always get what kind of number? What did our pattern suggest? It better be what kind? All day long we've been battling this. What is n plus 1 squared? How do you evaluate that?
N squared plus 1.
N plus 1 times n plus 1. You cannot make the mistake and say it's n squared plus 1. It says you have two of these things you have to multiply together. Now, what do we use to multiply two binomials together?
Foil.
FOIL. We'll take our first terms and multiply them together. What is an n times an n? N squared. We'll take the outermost two. What is an n times 1? Take the inside ones. What's a 1 times an n?
N.
And then we take the last terms. What is a 1 times a 1? Minus n squared. Now, is there any other simplification that we can do to this? Combine the like terms. So what are the like terms?
N. 3n squared.
The n's. How many n's are there? 2n. What else?
Whoa.
Oh, n squared.
Plus 1. What about the n squareds? The n squareds cancel. And what do we always get whenever we subtract consecutive terms? What is this going to be? Is that guaranteed to be an odd?
No, yes.
Well, if you knew what you were doing in your last quiz, that was definitely going to be an odd number. So therefore, it is odd. Okay, so that pretty much completes this problem. In letter D, they want you to describe the pattern of difference between successive square numbers as a proposition in the form if. If we subtract successive squares, or if you want to use the word consecutive, if we subtract consecutive squares, then the difference is odd. If you subtract consecutive squares, then the difference is odd. Very, very typical of the things that we're going to be working on. That's the easiest example they give us. From here, they get a little bit more complicated or difficult. So that's where we're going to stop today.